Hello, in this video I'd like to talk about the equation x cubed minus y squared is equal to 0, or x cubed is equal to y squared. If we're just plotting this in two dimensions, once we know what x is, that determines y up to a plus or minus, and once we know what y is, that determines x exactly. So it's a really simple graph. It's nice and smooth for the most part, except it has a singular point. It has a cusp at the origin. So that's not actually what I want to talk about. I want to talk about what happens if we let x and y be complex numbers. So let's focus on that situation there. So let's think about what it is that we're looking at in the first place, right? X and y being complex numbers means that they consist of both a real and imaginary component. So each of these variables actually has two real variables inside of them. So overall, the overall space is four-dimensional, right? There are four different real variables that can have all sorts of different values. The real part of x, the imaginary part of x, the real part of y, and the imaginary part of y. So that's four different dimensions. So overall, the overall space that we're working in is four real dimensions big, or we could also say it's two complex dimensions big, but that means that it's four dimensions of space. And then what we actually have here when we look at this equation is actually two equations of real numbers, right? When we say that x cubed is equal to y squared, we're saying that they have the same real parts and they have the same imaginary parts. And those are two equations. And if you wanted to, you could work out explicitly what those equations were in terms of how they relate the real parts and the imaginary parts of each of the variables with each other. You can work out what those equations are. But again, we have two equations of real numbers, that the real part of x cubed is equal to the real part of y squared, and the imaginary part of x cubed is equal to the imaginary part of y squared. And so each equation, and this is typical, although it doesn't always happen, but it does happen in this case, each equation drops the dimension of the solution set down by 1. So we have two equations. That's going to drop the solution set down from the dimension of the overall space from 4 dimensions down to 2 dimensions. So what we have here is the solutions to this equation are going to form a 2-dimensional subspace of 4-dimensional space. So how can we even start to visualize that or think about what that looks like? I mean, it's even difficult here in the format of video to communicate to you what a 3-dimensional thing looks like, let alone something in 4-dimensional space. So I definitely recommend that you head on over to trkern.github.io/knot. I'll link that down below, and actually play around with these. These are all created using 3JS, so you can rotate them around and hopefully get a much better sense of what's going on by doing the rotations yourself. So we're looking at a 2-dimensional subspace of 4-dimensional space, and one way of visualizing subsets of 4-dimensional space is by taking cross sections. What we can do is we can fix part of one of the coordinates, right? One of the coordinates in terms of the 4 dimensions, and it's going to be either the real part or the imaginary part of either x or y. It's going to be one of the coordinates, and then from that we can determine the possibilities for the rest of the coordinates. So here, this graph here, I have fixed the real part of x to be equal to 1, and then this axis up and down here is the imaginary part of x, and then once we know the real and imaginary parts of x, we actually know what y is up to a second root of unity, up to a plus or minus. And so what we see is that once we know what the imaginary part of x is, once we have both things for x, the possibilities for y are going to be located Well, what does it mean to be plus or minus in the complex plane? It means that they're on opposite sides of the origin. And so what we see here are two curves where one of them is on the opposite side of the origin from the other one. These curves extend off to infinity, but of course I've only drawn finite amounts of them. It's really difficult to draw infinite things. It's possible and it's fun, but it's really difficult to draw infinite things on a computer. But anyway, we have this plus or minus, and it's we can see how these curves, as the value of the imaginary part of x changes, we can see how they stay opposite the origin from each other. So one of these branches, one of these curves corresponds to the positive parts of the solution, and one of these curves correspond to the negative parts of the solution. And what we can do is we can change the real part of x. We can change where we're taking the cross section in order to see kind of an animation of this particular curve, kind of treating that as a time dimension. So we see that as we adjust the real part of x, we see these curves, well, they can come apart from each other. They can also, as the real part of x gets closer and closer to 0, they're actually going to get closer and closer to each other until we hit, I don't think we can actually hit, just because of the way the slider's set up, we can't hit 0 exactly, but close enough to 0, we see that these curves are intersecting. And this point here is the real part of x is equal to 0, the imaginary part of x is equal to 0, and the coordinates of y are also both equal to 0. So this is the origin in our four-dimensional complex space. And just like we saw before in our two-dimensional version of this, that point at the origin is actually a singular point. In this case, we can see that because we have these two curves that are kind of crossing through each other, and when they cross through each other, that's kind of what a singular point can look like when we're looking at it in cross section. But a really interesting thing happens when these two curves cross. They actually exchange branches with each other. So notice that the colors of these points, if we watch them in animation, haven't changed, but now suddenly our two curves, the two red pieces of the red curve have broken off from each other, and the two green pieces of the green curve have broken off from each other. And they've kind of done an exchange when they did that crossover. So that's kind of neat. And again, we still see this situation where once we know what, so we know what the real part of x is. Once we know what the imaginary part of x is, that is how far up or down they are in this direction, then that determines up to a plus or minus, up to a symmetry around the origin, what the coordinates of y are. So that's what this looks like if we're taking real cross sections. If we take imaginary cross sections, it's actually going to look almost exactly the same, right? All that we're doing is we're kind of rotating x by I, sort of. What that's going to do is just introduce a constant into this formula here, and that's just going to produce a constant rotation in y by some, it's not going to be some perfect amount. It's going to be some fraction of a whole rotation. And so this looks almost identical. I guess just the coloring is a little bit different. So instead of seeing the branches come apart, they actually switch colors. That just has to do with how everything works on the inside of this interactive. It was a real nuisance trying to get these things to look correct, just because there's a lot of inverse trig going on the inside here. So that was kind of difficult to work with. But anyway, we get exactly the same thing where we get these two branches that cross each other and do an exchange when they cross. It's just rotated a bit. On the other hand, if we take, whoops, let's move this over here. On the other hand, if we take cross sections in terms of the y direction, we're going to get something very different, right? X and y are very different in this equation up here. So here we fix the real part of y to be, well, about 1. This slider isn't perfect. And then this vertical direction here is going to be the imaginary part of y. And then once we know that, that's actually going to determine, well, it's going to determine x cubed, and then that's going to determine x up to a cube root of unity, right? So there's going to be 3 possibilities, right? Once we know what x cubed is, there's 3 different possibilities for the value of x. And of course, those 3 are all going to be kind of, rotated versions of each other around the central axis, and that's exactly what we see here. We see 3 different branches that are all kind of triangularly rotated versions of each other around the central axis. And again, if we take imaginary cross sections in terms of y, it's just going to be a rotated version by the appropriate fractions and whatnot. So taking imaginary cross sections in terms of y doesn't shed any more insight. But we can see what happens as we approach our singular point at the origin. We see that these curves all come closer to each other at 0, or well, close enough to 0. We see that these are all, they're all intersecting each other. And then we see actually that, this works out right, there we go, that again the threads get switched. So this isn't just threads crossing each other, there's some sort of exchange between these threads that's happening here. So that's one way of visualizing this particular, again, it's a 2-dimensional surface within 4-dimensional space. That's one way of visualizing it. Another way to visualize this, so here we're taking cross sections, but what if we take all of those cross sections and view them all at once? This winds up being equivalent to taking a projection, right? Imagine having a thing and you're taking a shadow of it. Well, then what you're really doing is you're just kind of adding together all of the different cross sections that all contribute towards the same shadow. They're all getting compressed down onto the axis and you're all seeing the same shadow. And so what we can do is we can show those projections. And it's going to be this really nice 3D surface. Ignore there's some gaps here just to keep some branches of inverse trig functions from going a bit haywire. But what we see here is we see a really nice, this is one entire surface. You can kind of trace your way around the entire surface. So it is a single surface that's kind of knotted in on itself around the origin, and it's radially symmetric. I view this kind of as a really complicated kind of flower. You have all of these petals that are, well, I guess, extending from kind of a single point at the origin, but they're actually just one really big petal that kind of loops in on. It's not really a flower, but it really seems like everything is kind of branching out from the origin. And if we want to take the, well, again, imaginary cross sections, it's going to look the same. This is exactly the same shape when we take the projection, when we, look at the sum total of all of these different cross sections that we're looking at. And then if we take cross sections in terms of y, we get a very different shape, right? Or projections in terms of y, if you take the shadow of something in one direction, it's not necessarily going to look like the shadow of that thing in the other direction. And so here we get a shadow of what we saw before, but now it's, this very different shape here. And again, we see that this is the sum total of all of these different cross sections here. And again, it is a single surface, right? You can kind of trace your way along the surface. When it crosses through itself, you kind of follow straight through, and that you can trace out the entire surface that way. So it's not a bunch of different planar graphs that are kind of intersecting each other. It's a single planar graph that's knotting in on itself. So this is, really kind of neat. It gives us a little bit more insights and practice working with visualizing these complex graphs, graphs in two complex dimensions. But I think that there's an even better way of getting an intuition for what this graph looks like. So what I'm actually going to do is, instead of taking planar cross sections of this graph, instead of intersecting with a hyperplane in this four-dimensional space, what I'm actually going to do is intersect with the surface of a hypersphere, right? Well, I guess, would you call that a hyperplane? It's not really a hyperplane, it's a hyperspace, right? When we're taking these cross sections, the cross sections that we're taking, this thing here, the cross section is 3 dimensions within a 4-dimensional space. And similarly, we want to take, if we, this you just kind of have to take this on faith, but if you have a 4-dimensional sphere around the origin, right, and so we kind of know what that is, just mathematically speaking. It's the set of all points in 4-dimensional space that are a particular distance from the origin. If we take that and we take its surface, well, just like how the surface of a 3-dimensional sphere is 2 dimensions, the surface of a 4-dimensional sphere is going to be 3 dimensions. Who knows what that even means, but mathematically it makes sense. The surface of our 4-dimensional sphere is going to be 3 dimensions, and what we're going to do is we're going to intersect that with the graph here. And if this helps, I don't know if this does, but we can visualize here what that hypersphere looks like when we take its cross sections. So of course, when we're taking cross sections where the real part of x is too big, here we're taking the hypersphere of radius 1. And when we're taking cross sections where the real part is too big, I guess. So one of the things that you can imagine that's really helpful to imagine when you're doing this is to imagine taking cross sections of a sphere, of a 3-dimensional sphere. Of the surface of a 3-dimensional sphere. So when you do that, well, of course, if you're too far out, you're not going to get any cross sections. Right? Imagine the sphere is here. Imagine we're taking cross sections here. We're not going to get anything. But at some point, is specifically at coordinate 1, we're going to start getting intersections, and those intersections, when we're doing cross sections of the surface of a 3-dimensional sphere, we're going to get circles. And the circles are going to get bigger and bigger as the cross sections go through the sphere, and then they're going to get smaller and smaller again once we pass the origin. And similarly, well, we're going to get cross sections, and those cross sections are going to be the outer surface of a 2-dimensional sphere. That's going to get bigger and bigger as we get closer and closer to the origin. And then when we hit the origin, they're going to start getting smaller and smaller again. So I don't know if this is helpful, but this is what we should be imagining here. And it's worth noting that while I'm talking about this, so all of this stuff comes from a book called Singular Points of Complex Hypersurfaces by John Milnor. And I just extracted kind of the most basic part of this book that I was able to understand, and that I think can be approached by a more general audience. There's a lot more in this book, but this is just the bit that I was able to get out of it. And it's worth noting, if you want to, this interactive also allows you to change the exponents here. So we can change from looking at x cubed minus y squared to looking at x to the fourth minus y squared, and it's exactly what you think should happen. You wind up getting, multiple branches. In this case, we have, again, 2 branches, and in this case, we actually have 4 branches, and they kind of do this same sort of interchange that we saw in the 3-dimensional case. So you can play around with the exponents as well, and again you get some sort of interesting behaviors, but not particularly enlightening. The thing that I think is a bit more enlightening in terms of visualizing this, again, is to take those intersections with the hypersphere. So let's actually think about this, right? So we are taking, in 4-dimensional space, we have a 2-dimensional surface, and we're taking intersections with a 3-dimensional a 3-dimensional thing, the surface of this 4-dimensional hypersphere. And what that means is that, right, the intersection is going to be a part of this 3-dimensional surface, this 3-dimensional space, the 3-dimensional surface of the hypersphere, and that intersection is probably going to be 1-dimensional, right? Doing this intersection has probably brought us down, and does in fact bring us down 1 dimension from a 2-dimensional surface in 4-dimensional space down to a 1-dimensional surface in 3-dimensional space. The same way that that taking these particular cross sections, these kind of orthogonal cross sections, brings us down from a 2-dimensional subspace of 4-dimensional space to a 1-dimensional surface in 3-dimensional space. So let's visualize that. Well, we actually need to be a little bit careful. So one of the really nice things is that we can explicitly solve for what these solutions look like. Here, if we're taking the intersection of the unit hypersphere, just the points x and y, whose magnitude squared, when we add those together, we get 1, right? That's what it means to be the surface of the unit hypersphere. And we're intersecting with our the equation that we're trying to solve, x cubed minus y squared. Let's go back to the x cubed minus y squared situation. So we're intersecting our sphere with the solution set that we're trying to visualize, and we can actually get a very explicit construction of what this winds up looking like. It winds up looking like some constant times e to the 2I theta, comma, some constant times e to the 3I theta, and then there's a plus or minus term. I'm writing this as z2 in the sense that it is a second root of unity, right? Here I say that z2 squared is equal to 1. So really what I could be writing here is plus or minus, but I'm interested in making this a bit more general so that when we go past this to think about other equations other than just having a 3 and a 2 here, we can kind of generalize it right away. So we can solve for what P and Q are if we want. Let's pop over here, and it turns out that all that we're solving for really is the intersection between this 2-dimensional graph, x cubed minus y squared is equal to 0, and the unit circle. We're looking for this intersection point, and we see that this intersection point is at 0.755, comma 0.656. These decimals go on forever, and there really isn't a nice closed form for them, I don't think. There's certainly not a nice closed form. There might be a closed form in this case. As these numbers get larger and larger, you're not going to be able to find a nice closed form for them. So anyway, we take those 2 numbers there, and those 2 numbers that we found, the 0.755 and the 0.656, are going to be the coefficients here, the p and the q in this equation that get multiplied by this e to the 2I theta. The e to the 2I theta here and the e to the 3I theta, those are just unit length complex numbers, right? They're on the unit circle in the complex plane. So we have these points, but they're still in two complex dimensional space. That is, they're still points in four-dimensional space. And what we need to do is we need to figure out how to map this this surface of the sphere. The surface of the sphere is three-dimensional. You need to find some way of mapping the surface of this the three-dimensional surface of this sphere here onto three-dimensional space. And it turns out that if we drop one dimension down, this question has actually been thought about a whole bunch. The question of how to take the surface of a three-dimensional sphere, which is two-dimension, like the Earth, for instance, and move that over to a two-dimensional surface, a map. And lots of people have thought about this question, and there's lots of different maps lots of different functions that will take us from the surface of a sphere to two-dimensional space. But the one that works best for this application is going to be the stereographic projection. And the idea here is that you can kind of visualize this. You have the sphere, and then you shine a light down at the North Pole. And then you kind of lay the sphere on a piece of paper, and then wherever the light goes through the sphere, it'll shine and give you shadows on the plane below the sphere. And that's really what we're doing. And this map is very nice. It's bijective. It's smooth, it is conformal, which means that it preserves angles. It is not space preserving, it doesn't preserve areas, but it does preserve angles, which is really nice. And we can do this, this same sort of projection from this three-dimensional surface of this four-dimensional sphere down to three-dimensional space. And again, the only way I have of thinking of this is in terms of, you just take the formula and you expand it and you hope that it works. So here we have this function here that maps us from this two complex dimensional space, four-dimensional space where we have A, B, C, and D, and then we map it to three-dimensional space where all of those are now real numbers. And here we wind up getting into a little bit of trouble when C is exactly equal to 1, but that only happens at one point on the surface of the unit hypersphere, specifically at just C is equal to 1 and everything else is equal to 0. And it turns out none of our knots pass through that point, so we don't have to worry about that. That point winds up getting projected to, well, a point at infinity, right? Because we're dividing by 0 in all of these coordinates here. So it turns out that the graph here is actually a very familiar graph, and a very nice, pretty graph. This thing here is called the Trefoil Knot. It is it's the simplest knot that we know of. So knot theory and mathematics, we're concerned about curves in space that are kind of knotted around themselves. Unlike typical knots, when you tie knots in ropes, they have knots in ropes have these two ends, but knots in mathematics, we kind of want to tie those two ends together so that we can really talk about undoing the knot. Whereas if you just have the ropes, mathematicians can kind of pull the knot out of itself and undo it. But this knot, you can't undo it by just topologically deforming it without having any crossovers. So this here is it's a trefoil knot. It's this very nice, pretty thing. And again, when we change the radius of the hypersphere that we're intersecting with, that really only changes the that really only does topological deformations to the trefoil knot. And the reason why that is because if the knot did cross over, so first of all, everything is smooth, right? The projection map is smooth, the intersections are smooth, the original shape was very smooth, so everything's going to be continuous. And so if the knot is going to change topology, what we're going to get is we're going to get a crossover. We're going to get two branches of the knot that either cross over each other or maybe do one of those weird exchanges. And that can only happen at a singular point of the original surface. And we can solve for the singular points of this original surface. And it turns out that the only singular point is at the origin. And so as long as we avoid the origin, and all of these hyperspheres do avoid the origin because they have some radius to them, and they're centered at the origin, we don't have to worry about intersecting any points where we see a crossover in the knots. So this is it. This is our intersection, and it gives us really nice looking pictures of knots as well. So what's going on here? Well, first of all, this knot here is actually a Taurus knot, and what I mean by a Taurus knot is that if we draw a torus of appropriate radii, the knot actually lies entirely in the surface of that torus. So this here is the appropriate torus. It's just, you take the projection of P times something on the unit circle, and Q times something on the unit circle, where P and Q are these. These are the numbers that actually give us the radii of this particular torus. And yeah, here we are. These are this knot falls entirely on a torus, so we call it a Taurus knot. And looking back at the parameterization of this knot, we can actually really have a pretty good interpretation of this formula here, right? As theta ranges from 0 to 2 pi, the e to the 2I theta, right? Remember that p is just a constant. The e to the 2I theta is going to circle around the origin twice. And that actually corresponds to this first coordinate here, the x coordinate. When we do the stereographic projection, it actually corresponds to how much we've gone around the torus this way, around the outside radius. So when we go twice around the outside radius, going from 0 to 2 pi, here e to the 3I theta goes from, it goes around the origin 3 times, right? It goes from e to the 0 to e to the 6 pi I. So it goes around the origin 3 times in the complex, on the unit circle in the complex plane. And that circle corresponds to these smaller inner cross sections, these smaller inner circles on the torus that go around the torus. And so what we get is we are every time we go around, right, so every time we go around this parameterization once, that is going from 0 to 2 pi, and then it repeats, we are going around the outside of the torus twice, and we're going around the inside of the torus 3 times. And that's exactly what we see here, right? Every time, it's a little bit tricky to see this, but every time we go around the torus twice, we're going around the torus this way 3 times. And you can actually see this a little bit better if we increase the amount of times it's going around the torus that way, right? So let's actually increase this up to, let's say, 13 here. So every time we go twice around the torus this way, we are going 13 times around the torus this way. And again, you can play around with these various coefficients, A and B. You can see that in some cases, what you actually get isn't a knot, right? A knot only has a single strand in it, mathematically speaking. A link, on the other hand, can have multiple strands. And so what we see here are actually two two really kind of trivial links. They're not knotted themselves, intersecting each other in a complicated way. And that's because there is a common divisor between 4 and 2. And so whenever there's a common divisor, that's going to give you multiple links here. We see 5 and 2 don't have a common divisor, so the whole thing is one single knot. With 6, there's a common divisor of 2, so there's 2 separate links. With 6 and 3, there's going to be 3 different links because, again, there's a common divisor here. With 7 and 3, there's no common divisor, and so, again, it's just going to be one single really complicated knot. So let's go back to 3 and 2. And again, you are welcome to play around with this. I definitely encourage you. You know, this interactive is free online. You can go there and just play around with it. One of the things that you might have noticed as I changed A and B, P and Q changed, but ultimately, you know, it's the same formula. It's going to be some constant times e to the b I theta, and some constant times e to the a I theta times the appropriate root of unity. So we get these really cool knots and these really cool links. And one of the questions that you might ask is, well, what kinds of knots and links can we get out of this process, right? We took the solutions to a polynomial, right? It was really simple polynomial. We started off with x cubed minus y squared is equal to 0. But as we changed a and b, right, that changed the exponents here. Right, a is the power, the exponent on x, and b is the exponent on y. And as we changed those, you know, we got different knots and different links as a result when we did that. And so one of the questions that you might ask is, well, what if this were some other sort of polynomial? What sorts of cross sections could we get by doing this? And this is a really wild question, but it's actually something that's really important that mathematicians really care about, and they also care about this question in higher dimensions, right? So, I mean, this is as far as our imagination can possibly take us, but it's still an important question. What happens when we have these singular points of complex hypersurfaces, singular points of, you know, the solution to some sort of complex polynomial equation? And, you know, what's going on at those points? Even if that equation involves maybe a whole bunch of different variables, right? So instead of having, you know, 2 variables gave us 4-dimensional space, what happens if we have, like, I don't know, 5 variables and we have 10-dimensional space? What's going on there? What can we do to talk about the topologies of those things? You wind up doing sort of knot theory in 10-dimensional space, which is kind of neat. And you can, you know, study the topological properties of these knots, and you can come up with, you know, there's lots of things that we do to study these knots. We talk about knot invariance and various numbers and polynomials and things that are associated to knots to help us determine when 2 knots are different. And it turns out you can solve those for these particular things using some algebra, once you have an algebraic description of these knots. So again, we ask the question, when we take the unit hypersphere, or an appropriately small hypersphere, let's say, and intersect it with a polynomial, here, you know, something weird might be happening if we take large hyperspheres. There might be multiple singular points inside. With these types of polynomials, we don't have to worry about there being other singular points. But let's say that we just want to focus on one singular point. And so if we're talking about general polynomials, They might have multiple singular points. So let's just focus in on one particular singular point. We'll take a sphere around that singular point that's small enough so we're only focusing in on that one singular point, and ask the questions: what sorts of knots can we get, or links, when we do this intersection, when we take the intersection of these things? And the answer is something called a compound cable knot. The idea is that we start with the unknot. We start with just a basic circle, and then we take a neighborhood around that circle. And within that neighborhood, we draw some sort of spiral. And that's exactly what we have here, right? These knots here, these torus knots, are just, you take the unknot, um, and we drew a neighborhood, specifically this torus. We drew that neighborhood around the unknot, and then we just kind of twisted our way around that torus some number of times. And it's, we twist some number of times around in one direction every time we twist some number of times around in the other direction. And that gave us all of these different knots here. But then we can continue that process, right? So instead of drawing a torus, let's go back to the trefoil knot, right? A is equal to 3, B is equal to 2. And what we're going to do is we're going to draw a tiny little neighborhood around this knot. And we can do this around any knot, right? A and B can be whatever we want. So we can have all of the knots and links that we've seen before. But let's just do this with the trefoil knot. We're going to draw a little neighborhood around this trefoil knot here. This doesn't work out very nicely. But the reason why it does is actually just because of the space distortion of the stereographic projection that we're using in this case. It's actually a very nice neighborhood that we're looking at in this situation. So we have some neighborhood, and again, these are knots. We're only concerned about the topology of everything, so we don't really care about the shape of these neighborhoods. We're just concerned about that we have these neighborhoods, and what we're going to do is within that neighborhood around this trefoil knot, where again we're going to be spiraling around our trefoil. We're going to just be spiraling around. We'll spiral some number of times around this way every time we spiral some number of times around the knot itself. And provided that we do that, we're going to get a second order torus knot. And we can keep going, right? We can draw neighborhoods around that knot and spiral around in those neighborhoods, and draw neighborhoods around that knot and spiral around in those in those. And when we kind of take all of the knots that can be obtained in this particular way, we get something which are called the compound cable knots. And these are the knots that can be obtained by looking at singular points of complex hypersurfaces, singular points of, well, I say hypersurfaces. We're really looking at varieties here. We're looking at the solution sets to polynomial equations in complex numbers, and again, we're taking tiny little spheres around the singular points that we get from those equations, and we're looking at what kind of knots we get when we do these intersections. So let's go back to this very concrete example. Let's draw a knot that kind of spirals around within this neighborhood around the torus knot. So let's do that. So it's a little bit hard to see, but this black knot here, this black line knot here, every time we spiral twice around the torus knot itself is going to spiral 3 times around in this kind of circular neighborhood. And this is easier to see actually if we bump this up. So let's bump this up to something like, I don't know, 33. And now we can see really what's happening, right? This knot here is spiraling around 33 times this neighborhood every time we go twice around the knot itself. And again, it's very similar to the original construction of these torus knots, where again we could spiral around a whole bunch of times and really kind of get a picture of what was going on. And again, we can spiral around these knots that were produced, and we can spiral around the knots that are produced in those processes, and so on and so forth. So why should we believe that this knot here in black can be obtained by taking the solutions to some sort of polynomial equation and doing this intersection process. Find a singular point at the origin, although if it's not at the origin, you can kind of move everything so that it is at the origin. But to take a singular point and take the hypersphere around that singular point and do this intersection process and do this projection process, why can we believe that we can get this black knot here that spirals around? Why do we believe that we can get that out of this process? We can see this if we look at the parameterization of this knot. And what we do is we just take the original formula here for the original trefoil knot, and then we just add a new little term here. So this is going to be epsilon. Epsilon's going to be the distance between the spiraling around knot and the original knot. In this case, it's 0.1. Epsilon should be small, but it doesn't have to be too small. The important point is to keep these spiraling bits of one part of the knot from intersecting with the spiraling bits of another part of the knot, right? If we have two pieces of the knot that kind of go near each other, we don't want their spirally bits to collide with each other or somehow get knotted with each other in a way that we don't want. So it's important to pick epsilon to be small. It doesn't have to be super small. We're going to do epsilon times e to the, in this case, 33 halves, because we want it to spiral around 33 times every time it spirals around twice. So we're going to do e to the 33 halves I theta times an appropriate root of unity. Again, this z2 is just representing plus or minus 1, but if we change d, we're going to get some other root of unity here. This no longer is on the unit hypersphere, but we can actually, it's just slightly away, right? If epsilon's small, this is just slightly off of the unit hypersphere, and we can, by kind of deforming everything just a little bit, we can get back onto the unit hypersphere without, and again, if epsilon's small, this won't change the hypersphere going back from the deformed version that this graph is on onto the deforming back into the actual unit hypersphere, or epsilon hypersphere, or whatever we're working with. Doing that deformation isn't going to cross any singular points, again, provided that we picked epsilon small enough. And again, the way to think about this is we don't want these twisting strands to have to cross each other when we do this deformation. So ultimately, we can deform this without changing the topology of the knot. And again, the only question is, topologically speaking, what knots can we obtain in this way? So this is perfectly fine. We now have to see, why is this, so these points here fall on the unit, well, sort of on the unit hypersphere. But why should we expect these things here to be the solution to a polynomial equation, to some sort of complex polynomial equation? Well, here's the clever bit. So we notice that both of these things here, this and this, are both polynomials in e to the I theta over 2. And all we need to do really is prove that if we have two polynomials, I guess there's some tricky bits with these plus or minuses that we have to worry about, but essentially if we have two polynomials in the same variable, in this case e to the I theta over 2, we just need to show that they have a polynomial relationship to each other. And the idea here is that you have two polynomials, let's say, let's call them f and g, in a variable, let's say x, for instance. Then all you need to do, it really is consider how the dimension of this thing grows as a vector space, right? The dimension of polynomials of degree n in x grows well, it grows exactly like n. And the monomials that we can get by taking f to some power and g to some power that have degree in x less than n, you can show that this grows as O of n squared. The exact big O is a little bit tricky. I've linked down at the bottom of this interactive to a Math Overflow answer that actually works out explicitly, all of the explicit numbers, which is really nice. But the idea is that this collection of uh, uh, f to the n times g to the m grows as O of n squared. And so eventually we're going to have more things in this collection, right? Things of the form f to the n times g to the m in this collection than we have dimensions in our vector space. And so we have a linear relationship among the f to the n, g to the m's. And what is that? Well, we call that a polynomial relationship between f and g, and that's exactly what we're looking for. So this turns out here to actually be the solution set, or at least part of a solution set, but you can show that it's the solution set to some sort of polynomial equation among x and y when we're looking at these things in terms of complex numbers. So I think that's really cool, right? We're trying to do this really kind of abstract thing, and we just have this really neat collection of knots. We can produce these really nice pictures of knots, which I think is really kind of the fun part of doing all of this. And there's also a whole bunch of really deep mathematics going on here of trying to understand these knots. Can every knot be obtained as a compound cable knot? That's an important question. How do we tell if two of these knots are the same, right? Maybe we have one process that does a bunch of compound cabling in one way, and then another process that does a bunch of compound cabling in another way, and we ask, are these two the same? There's a whole bunch of really interesting knot theoretic questions that we can ask about in this particular way. So I hope you enjoyed this video. Feel free to stop back on this channel. Every so often I will post some mathy videos for you to enjoy. I might also post some videos about teaching because I also care a lot about teaching. So just be aware, it's not all going to be math videos. Some of these might be teaching videos as well. But I hope you enjoyed this. Again, feel free to check out trpern.github.io/knot if you want to play along with these things and rotate these images yourself. And thanks for stopping by. I hope to see you in a future video.